So we're live on YouTube
Okay.
and we're broadcast.
Okay, so welcome everyone to the afternoon session after a short lunch break. Before we start and I will introduce the combatants, I would like to advertise the special issue. 1 second, I will share my screen here. Cannot. Okay, can. I would like to advertise the special issue, topic issue in European Physics Journal D on quantum aspects of attoscience, with several aspects here, which were also focus of this conference, from attosecond imaging over chiral light and free electron lasers, with a submission deadline end of the year. And if you want to know more, you can either contact Carla or Andrew, who will be one of the combatants here also in this session. So, and with this short advertisement, I would like to introduce the combatants of today. So I will put it in the list as it's online. So at first here is Emilio Pisanti. Emilio.
Hi, my name is Emilio Pisanti. I'm a postdoc in ICFO, the Institute of Photonic Sciences in Barcelona. I work on analytical methods, on SFA for HHE and ionization, and also going into optics and structured light.
Thank you, Emilio, and welcome. The next on my list is Andrew Maxwell. Andrew?
Hello, I'm a postdoc at UCL. I'm a combatant in this session, but also one of the organizers. I also work on analytical methods such as Coulomb-corrected methods in holography, NSDI, and other quantum effects.
Thank you, Andrew. Next person is Margareta Kochlova.
I'm a postdoc at Max Born Institute right now. I used to work on HEG and resonant HEG, in particular before creation of more efficient attosecond sources, and now I'm working mostly on their application.
Thank you, Margareta. We have next Greg Armstrong. Greg?
Hi, I'm Greg Armstrong. I'm a postdoc at Queen's University Belfast. I'm working with the R matrix with time dependence method to study strong field ionization of multi-electron atoms in arbitrary laser fields.
Thank you, Greg. We have Marco Roberti.
I am Marco Roberti. I'm a postdoc at Imperial College London. I work on the development of ab initio methods, in particular B-spline TDSE, to study attosecond ionization dynamics of many electron correlated systems.
And last but not least, we have Marie Labeille.
Hi, so I'm Marie Labeille. I'm an assistant professor in Paris at the École Normale Supérieure, and I used to work mostly on harmonic generation, but more recently I've moved to new sources like XFELs and seeded FELs.
Thank you, Marie. So the topic of the last quantum battle is not experiment versus theory, whether we need it, but we are within theory. And the topic will be numerical versus analytical methods. And Andrew, would you like to start screen sharing? Or who was it? Yeah, okay. And we have 3 questions for today. First one, what are ab initio methods, analytical methods, and in between? A second, what are the advantages and disadvantages of the analytical and ab initio molecular numerical methods? And what does scientific discovery look like in our field? So I would like to hand over to the combatants. Start on this part. We'll start.
Okay, thank you for the introduction. So we're gonna start this battle by setting the scene. So describing, introducing what are ab initio, analytical, and in-between methods. In particular, let's start from the definition of ab initio. So ab initio is the Latin for from the beginning in English, meaning from first principle. So we aim at solving a physical process from first principle using the most fundamental laws of nature that we understood govern the physics. And so we aim to have as input in the calculation only physical constants and to keep the interaction between the particles or the subsystems as fundamental as possible without making additional assumptions on top of what are the established laws of nature and without using spatially tailored models to tackle particular aspects of the process. But this, of course, leads us to the question, what does fundamental mean? This, of course, is like setting a reference frame in what we mean by as fundamental. We can go from a single active electron description in quantum mechanics using Schrödinger equation and using a classical description of electromagnetic field. Then we can, of course, take into account the many-body nature of our problem and using non-relativistic many-body quantum mechanics, for example, still describing the electromagnetic field classically. And then we can, of course, introduce relativistic effects and go all the way down to quantum electrodynamics and, in principle, quantum field theory for nucleons, electrons, and the electromagnetic field, which is, in the end, the basic theory that governs everything that we are describing in attosecond physics. And most of the works, if you could go back to the previous, thank you. Most of the works happens in this region where you have when we basically either describe we model our system by using a single active electron approximation, or we describe we take into account the many-body quantum nature of the systems that we describe, but using mostly non-relativistic quantum mechanics. And so how do we take into account the many-body nature of the systems, for example, electrons in a molecule, in an atom, or in a solid that we want to describe? So starting usually from mean field theories, like R3-Fock methods or the density functional theories, then we can improve the description of the electron correlation by using either post-R3-Fock methods or time-dependent density functional theories. And we can go all the way to a full description of the correlations, which in a quantum chemistry language that would correspond to a full configuration interaction in a complete basis set. Of course, when we are doing this, we always have to face a trade-off between an accurate description of this correlation and the computational effort that we are required to put in. And I hand over to Emilio.
So that brings us to the analytical methods, and here it's maybe a softer and squishier definition. So generally, we think of analytical methods as those that we can analyze using just pen and paper. Maybe more formally, we can try and pin it down to models in which the solution or the observables can be expressed in a closed form, or that we can write down. But then I would argue that this needs to be thought of more carefully, and particularly what do we mean by closed form? Is it just elementary functions, so just exponentials or logarithms, or do we allow special functions? And what does special function mean? So there's one poll on Slack and on Twitter kind of exploring that boundary, and I would argue that it's a very squishy boundary. Do we stop at Bessel functions? Do we allow hypergeometrics? Do we allow MyGRG functions? Do we allow freshly minted special functions? And you can try and turn to the mathematicians to answer this question, and there are no hard boundaries. There are no objective classifications which are useful and universal, and it's more of a shared language. It's more how we communicate and encapsulate concepts with each other, and this is being written about very cogently in the paper that is referenced on the bottom right. And I think it's worth thinking about more carefully. In our field, and if we can move to the next slide, it's also important to remark that analytical does not mean approximate. And there are plenty of quantum systems, simple ones, but important ones that we can solve analytically. They're generally the ones we're taught in undergraduate physics. So the harmonic oscillator, the particle in a box, but also the hydrogen atom is an ab initio exactly solvable system, as is the free particle, including the electromagnetic field. And this can also be done, if we allow for perturbation theory, through to fully working analytical methods, including single and few photon ionization and excitation methods, as well as start shifting, giving rise to dipole forces and so on. And if you go more into quantum field theory, Feynman diagrams are perfectly working analytical methods. In our field, more generally, the methods that we think of as analytical can be split into fully classical, semi-classical, and fully quantum. So the fully quantums are the strong field approximation in its full time integrated glory, but also in semi-classical methods when we do saddle point approximations and moving into quantum orbits and also Coulomb correcting them and so on, and moving down into simple Man's model classical trajectory methods. But I would argue, and I think several of us would argue, that these are not actually analytical. If we're doing classical trajectory Monte Carlo, we're involving a massive numerical effort, often in doing ensemble averages over lots of classical trajectories, which we cannot actually solve, and we need numerical efforts to solve those equations. And the same must be said for the strong field approximation and so on, where we have saddle point equations which we need numerical methods to solve. And particularly for Coulomb-corrected SFA, the work involved both analytically in kind of pen and paper work as well as numerical work can be higher than some numerical methods. So the question is, are those still analytical? And what happens when we can solve perturbation theory analytically, but we need quantum chemistry to give us matrix elements, and that also involves lots of numerical work. And this kind of gives rise to the distinctions between numerical and ab initio as well. Marco, you're muted.
Yeah, so and now so leads us to discuss the fact that, as most usually maybe it's assumed, numerical doesn't necessarily mean ab initio and the other way around. There are many numerical methods which are not ab initio, for example, single active electron approaches, which neglect electron correlation, and which usually require semi-empirical modeling of the effective potentials that represent, for example, the mean field interaction of one electron with all the other electrons in the system. Density functional theory and time-dependent density functional theory are in principle ab initio methods, but when we don't know the exchange correlation functional, then, and we use a semi-empirical parameterization for this functional, then we have a guess at the interactions, and then we are not formally in an ab initio framework anymore. And also working in reduced dimensionality, for example, one-dimensional, two-dimensional models also can affect the physics. And this leads me to the second slide, though, which is also important to think about, which ab initio doesn't necessarily mean exact, on the other hand. For example, ab initio methods can give a very different level of accuracy depending on the approximations that are introduced into them. However, what they offer is a systematic way of improving this accuracy, which doesn't rely on semi-empirical fittings or parameterization. And so this gives to ab initio methods higher fidelity in a way. So when we change the system, we are confident, or kind of confident, that we're going to get the same accuracy that we, at the same level of accuracy that we get for other systems as well. Then, of course, as I said, electron correlation can be included at different level of approximations, or can even be neglected in, for example, in our Trifoc ab initio method. The basis set that we use is basically represents the subspace of the solutions that we are looking for in our problem, can be optimized by even fitting procedure, sometimes to speed up the convergence toward the exit, so toward the exact solutions. Although this procedure is not necessary, it's just to speed up the convergence toward a more accurate solution. And sometimes we also introduce pseudo potentials. So we have an ab initio methods, but we don't want to describe everything ab initio. For instance, in a molecule or in an atom, the effect of core electrons, or sometimes the effect of in a relativistic regime or spin orbit interaction, or orbit interactions. So then sometimes we use pseudo potentials to model these effects within an ab initio framework. And this leads to what I think are hybrid methods. So they're not fully ab initio, but they have a very strong ab initio flavor. And then I hand over again to Emilio.
So these hybrid approaches can be as simple as rate equation approaches, where we use cross-sections from ab initio methods, but we discard the coherence, and this is extremely widespread in some fields, particularly when boxed up as molecular dynamics approaches. And it can also be used for SFA and related approaches, where we can expand them using multiple channels, but we need the energy levels and the dipole moments from a quantum chemistry calculation. And there are also fancier and newer approaches, like Hongcheng Ni's propagation work, where you morph from a TDSE output to a classical ensemble, invoking some of the tools from analytical methods, but also deeply reliant on numerical methods. And actually, if you can go back 2 slides, just to comment briefly on one more. So we've been keeping an eye out on how these terms have been used during the conference, and we've kind of spotting the term ab initio in the wild, and it's been used both exclusively for correlated multi-electron stuff, and as well as earlier this morning, calling DFT an ab initio solution. So it's interesting to note what this means, and if we can go back again forward. What we want to say, I think all of us, is that this is a spectrum. It's a spectrum between fully analytical on one side and fully ab initio on one side, and more generally between fully and completely not analytical, and between fully ab initio and not ab initio at all. And there's a bunch of methods that we use on the field, and we've put them in vaguely indicative positions here. I suspect that people will disagree with where we've placed them, and if you do, then please put them in the Zoom chat or Q&A or in the Slack channel. There's a bunch of methods here, and it's important to keep an eye that analytical and ab initio are not incompatible and are not black and white distinctions. And I would also go forward with perhaps more contentious, more provocative claim that the useful distinction is not whether a method is ab initio or analytical, but that the distinction is whether the insights we get from that method are of a quantitative nature or of a qualitative nature. Ab initio methods are great in matching quantitatively to experiment, but we often don't understand the systems well enough, and we get qualitative insights much clearly from analytical-like methods. To some extent, the term qualitative is I feel stigmatized or carries a lot of connotations that are very negative. I think often we, in physics, at least in parts of Europe and the US, we use it to make ourselves feel better about how much better physics is to biology or social sciences. And I think that we have a lot of work to do as a discipline destigmatizing this name. There's a lot of value in qualitative descriptions or qualitative insights, and we should cherish that. So we have we're posting a poll on Twitter, and also should come up shortly on Zoom regarding what people think about this distinction. I'm not sure whether this already open. Oh, there we are. So
yeah, there's a poll.
The distinction of methods that provide quantitative versus qualitative insights is more useful in practice than the analytical and ab initio distinction, and we're interested in knowing what you think. And yeah, I think this is the end of the first question we wanted to tackle, and we now move on to Andy and Greg, who will discuss the second question.
So I think it'd be good to see the results of the poll as well after giving everyone a moment to vote on it.
Yeah.
So I don't see results.
So people are still voting currently. We're about halfway there.
So while we wait for people to vote, I can introduce the next part, which is essentially what are the advantages and disadvantages of analytical and ab initio methods. And to do this, we're going to use non-sequential double analyzation as kind of a case study to highlight these advantages and disadvantages. And it's kind of an ideal process, given that for both it's quite difficult. For ab initio, it's only recently that computational power has got to the point where this is possible. Oh, the results are in.
Yeah, here we have the results. Maybe I shortly comment. So 84% agree and 16% disagree. So it's more or less quite clear statement.
Yeah, that's actually surprising to me. I propose that distinction being quite provocative, and I'm not sure I fully believe in it myself. I think it's useful, but it's interesting to note just how skewed these results are. And I think maybe that's indicative that we should rethink of how we think of this as a community.
Do we know how many people voted? Is it significant?
38 votes.
Okay.
So let's go to the second. I'll hand over to Andrew.
So as I was saying, non-sequential doubleization is an ideal case study for the advantages and disadvantages of numerical methods. Ab initio because we've only just been really able to get the computational power to model it, and analytical because it's been quite a long road to develop good enough methods to do that. And now I hand over to Greg.
So I'll outline some pros and cons of ab initio numerical methods, particularly in this context of NSTI. The first pro is that these problems are now more efficiently tackleable. Efficient methods have been developed over recent years to tackle these problems, and despite the fact that they're typically large scale. And with these methods at hand, it encourages the development of alternative methods, which perhaps stop short of a full ab initio treatment, but are nonetheless insightful. And finally, with a general enough approach, you can apply a method to a wide range of physical problems of interest. On the con side, of course, interpretation can be difficult, the complex outcome from a TDSE calculation, for example, and also direction can be needed in advance of performing big calculations. And also, if the calculations are of large scale, you really need to consider and justify the scale of your calculations before proceeding.
So for the analytical methods, I would say one of the main pros is that it's a modular tool where you can switch on and off parts that you can use to understand the physics intuitively, where you can match parts of the model to the physics. Also, generally, they can be solved faster and scale better with degrees of freedom, which allow you to do extra computations, which would be impossible with ab initio methods because it would take too long. Analytical methods can also direct more expensive ab initio or experimental efforts due to these previous pros. And on the negative side, approximations can at times make the results inaccurate, sometimes entirely missing certain details. And the approximations you make, it may be unclear how this will affect the physics. Also, analytical methods tend to have a lack of generalizability. So often you'll need to change the approximation in order to explore different parameter ranges or change the system in some way. So as I said, we're going to use non-sequential double lonization as a case study, and Greg will go over the two different mechanisms.
So non-sequential double ionization is an important process in strong field physics. It involves the interaction of an intense field, typically 800 nanometer wavelength, with a system. And this field initially ionizes a single electron. That's the blue electron shown in these figures. This single electron is driven first by the field away from the ion and then is returned to the ion as the field changes direction. And as it recollides with the parent ion, double ionization can be mediated by a variety of processes. The two main ones are illustrated here. On the left, when the returning electron is sufficiently energetic, it can knock out a second electron in a recollision process. This is the recollision impact ionization scenario. Or on the right, if the recolliding electron is less energetic, it can excite the second electron, which is then subsequently ionized at a later time by the field. And this is the RESI scenario. And these are two of the main pathways to non-sequential double ionization. So I will now outline the application of ab initio numerical techniques to this problem, highlighting their pros and cons. So the first pro is that numerical methods for tackling this problem ab initio are now at hand. Methods for direct solution of the two-electron time-dependent Schrödinger equation have become increasingly more efficient in recent years. And this problem in particular is a notoriously daunting one. In 2006, calculations could be done for double ionization of helium at 390 nanometers, and where they calculated the momentum distribution shown on the left here. Now, this calculation took an entire supercomputer, all 16,000 cores on the Hector machine available at the time, with runtimes in excess of 24 hours. And that's a massive computational expense, obviously, despite the fact that the helium code used for these calculations was an efficient method. But by 2016, calculations could be done for double ionization of helium at 780 nanometers using the T-surf method of Armin Scrunzi's group. And the calculation shown on the right here took 128 CPUs for 10 to 12 days. That's an order of magnitude reduction in the computational demand between the two calculations, despite the fact that the calculation on the right is actually a tougher problem. They're doing 780 nanometers rather than 390. So it's a much more complex problem. So methods are now at hand for tackling these things in a more efficient way. The second pro is that calculations like this can encourage what I call intuitive alternatives. The main difficulty with all two-electron TDSE calculations is the high dimensionality. And maybe treating it in full dimensionality is overkill. Reductions may be possible and justified. A variety of attempts have been made at this. One case that's interesting in particular is a calculation from 2006, where the two-electron system was considered with the center of mass fixed to the laser polarization axis. Intuitively, that seems reasonable, given that it is the center of mass that couples to the linear field. A calculation of that type took 20 hours on one CPU in 2006, same year as the helium calculation. So making these subtle reductions can drastically reduce the computational time, and it would be interesting to know through comparison with the full solution if such things are justified. So the third pro is that with a general enough method, you can apply it to a range of problems. And I'm showing here 3 calculations that I've done with a time-dependent close coupling approach to the two-electron TDSE. On the left, a multi-photon calculation with the helium code. In the center, the simpler problem of two-photon double ionization with time-dependent close coupling method. This is still, although it's a simpler problem, it's still important for application and support of experiments at FLASH, FEL. And on the right, electron impact processes can equally well be treated by the same method. In fact, there's a whole plethora of calculations done with this method and its variants, and there are review articles on the subject. So on the con side, interpretation can be difficult. The outcome from a complex TDSE calculation can be extremely involved, and it can be difficult to disentangle all the physical processes that are wrapped up in the solution. To do this disentangling, you need sufficient tools within your method and switches to aid your understanding. Even with those at hand, it may be an arduous procedure because it may require many large calculations. Secondly, on the con side, if calculations are large, you really do need to consider and justify the necessary scale before proceeding. It's good to ask as early as possible, is it worth it to actually do these calculations? Calculations shouldn't just be feasible, they should also be justifiable. You also obviously need to consider what scans you may have to do, intensity averaging, etc. Also bear in mind that the computational cost can scale very unfavorably with certain laser parameters, for example, the wavelength, which means that success at 800 nanometers, say, may not translate into success at 2400 nanometers, where experiments, as I'm showing here, are being done. And that needs to be borne in mind before proceeding with calculations.
So now we move to the analytical, highlighting the pros and cons. So the first pro that I brought up was the modularity of the analytical models. And I show here again the experimental results that were shown yesterday, where you have an increasing pulse length, which causes the momentum distributions to go from a cross shape to anti-correlated. And along the bottom, I have the SFA model that we used to model this via taking a superposition of different excited states in the Resi mechanism. And this was only possible because we could switch on interference effects, switch on and off interference effects that enabled these different shapes. And we were able to directly attribute momentum shapes to different excited states in momentum distribution. So it kind of shows the power of the modularity and understanding the physics intuitively with the model. This model was also able to be solved in 5 minutes on a desktop computer, where we saw that an ab initio model would take days on hundreds of cores. And this allows computations such as focal averaging, which would add 10 times to the runtime or more. And also, more importantly, an in-depth scan through intensity and frequency, where we're able to further validate our predictions by doing kind of a frequency analysis of the pulses. And this would add, 100 to 1,000 times to the length of runtime for the computation, which would just be totally impossible with an ab initio method in this case. And off the back of kind of similar SFA results to that, experimental work was done to investigate interference effects. And so it shows how the analytical methods can direct these more expensive approaches such as ab initio or experimental efforts. Of course, on the negative side, the results can be inaccurate. So the SFA neglects the Coulomb potential, and then there's this famous result of the finger-like structure in NSDI. And it's known that the Coulomb effects will affect the final momentum distribution. So you do have to be careful with the conclusions that you draw from such an analytical model. And then I bring again this ab initio plot where we have mixed in together all different processes. So you have kind of the Resi mechanism, but also the electron impacts mechanism or RI mechanism, as well as double ionization. And the SFA model presented only described the Resi mechanism, and you would require a new model to describe each of these processes. So although it's nice we can separate the processes, it's also kind of a lack of flexibility of the model that you have to particularly set up on it at each time. But then just to kind of summarize this, the benefits of using both these kind of models outweigh the risks for sure. So in the case of classical and semi-classical models, they have led to huge leaps in understanding for the mechanisms of NSDI in terms of the three-step model. Also, efficient numerical methods now mean that ab initio calculations can be carried out more readily and are well worth going for. But of course, the best way to protect against the inaccuracy of analytical models and the difficult difficulty to interpret results in ab initio methods is just to use both types of methods.
And finally, as a sort of unifying point, it may be that NSDI in particular is a good candidate for hybrid models, where strongly correlated dynamics and multi-electron effects are suited to an ab initio approach, and there are other elements where you could bring in semi-classical models in a hybrid method.
So now we have another poll where we essentially...
Before we go to the last poll, I would like to read one of the questions coming in, which is a criticism of your last poll, which is stated to be let's say, a rhetorical question, because the question was verbally placed on the answer yes. So this exomol group claims that the drastic ratio of A versus B was mainly due to the way the question was written. Let's see how it will be now on the next poll. So the question we have here is, would you feel more confident in planning an experiment based on guidance from analytical theory, ab initio simulations, or a hybrid model? So here you can place your favorite method, and let's see what comes out here. I hope that also experimentalists contribute here to the question, and not only those who have already a predefined opinion, like the combatants here. I think here the question was stated more neutral. So here's really, you can place what you want. So I have here the outcome.
Oh, it was close.
So we have here 19% preferring analytical guidance, 38 prefer ab initio, and another 43% prefer hybrid. So we didn't ask for qualitative versus quantitative. And with this statement, I would like to hand over back to the combatants.
And so now we'll try to look at our third question. So what does scientific discovery look like in our field? And we'll also go through this question with an example and a case study in head. So the case of resonant HHG. And we'll try to run through this very nice story of resonant HHG step by step. And we'll start with an experimental mystery or puzzle, if you like. So you can go to the next slide. So the experimental kickoff of resonant HHG. So HHG was already known, but some features in HHG spectra, for example, plasma plumes or helium spectra or noble gases, were still unexplained. And in particular, the fact that you could see resonances at particular harmonic orders. So this really started a whole history of resonance HHG. So how could we explain such resonances that appear, so either in plasma plumes or at specific energy in helium, or even on a broader scale in, for example, xenon?
First clue comes from this broad, well-known enhancement in the spectrum of xenon atom, which was predicted first theoretically and connected to this giant resonance in xenon recombination cross-section. The next hint comes from the helium experiments. Both of enhancements in the harmonic spectrum can be connected to the strong transitions with a strong oscillator strength in the spectrum of helium. And those transitions are the transitions between the ground state and ionizing state. And finally, for the plasma plumes, as well, we can see here that the strong resonant emission of the harmonic also is connected to the appearance of this strong transition in this case, indium ion. And all of these observations and hints give us a chance to formulate a model of this process, which is four-step model, and this four-step model is some kind of similar to three-step model. So first step is also ionization, then electron travels in the field, and when it comes back to the parent ion, instead of recombination, it first gets captured into autoionizing state and then relaxing to the ground state, emits this harmonic with more efficient harmonic. And
so now that we have a model, it would be great to make sure that that is really what happens in the experiment. So the first step is to compare with numerical, like single active electrons, so approximated numerical models that were performed by Strelkov in 2010 and Tudorovskaya and Manfred in 2011. And so they first were able to reproduce this enhanced intensity of a particular harmonic of the spectrum. So that was more maybe of a qualitative agreement. But now what about a real analytical model that could really explain what is happening?
so analytical theory was built on two pillars. It is Levenshtein's SFA for HEG, which can be treated as some conventional theory, and to include multi-electron effects, the configuration interaction here. The Fano theory was used. This treatment merge of those two theories gives us a chance to describe the harmonic spectrum as a factorization of the high harmonic Levenshtein's spectrum times some factor which is the same as conventional harmonic spectrum far from resonance and has a Lorentzian shape around the resonance. And the parameters of the resonance are included within the parameter, which is similar to the Fano parameter is his theory.
And so again, once that we have a model, it's always good to make sure that it's convergent with respect to the previous one. So here is a comparison between this analytical model and the previous numerical result that were obtained with the single active electron TDSE, and it's really a good match. So both on the intensity and on the phase of the harmonic spectrum, and so we really have an agreement and a validation of this model at that point. But now a good question would be, a real validation of the model would probably require ab initio and real quantitative numerical simulations. So what about ab initio? Where are we now?
So this last needed step was done also very recently published, and the group of Kenichi Ishikawa conducted the calculation, first principle calculation for high harmonic generation in manganese ions, and they reproduced this enhancement of harmonics around the resonance. So these results first agree with experimental results, but also as ab initio results, they give us a chance to see which transitions in this fully correlated model system give more or less contribution. So I think here we can, on the one hand, put a full stop in the mystery of the mechanism of the process and open a new field of applications of resonant HEG, which seems to be quite fruitful because of its interesting features.
We can't hear you, Mary.
Sorry. So to conclude, we would like to emphasize that we all depend on each other. So of course, theory and experiments. So in this particular story, it was really experiment that started the whole thing with an experimental mystery, but we could have told you any other stories in strong field physics, and it could be really worked the other way around, where theory predicts a process that experiments try to observe. So for example, in the case of rabbit or other possible stories, but it could also be more entangled, where both work together close in hand, where you could have a theory identifying maybe a specific parameter range where the experiment would discover new part of a phenomena, or experiment could confirm or give some parameters to fit some specific theoretical models. And also within theory, also the different approaches that we can take in theory also depend a lot on each other. So in this particular story, it really started with approximate numerical methods together with analytical method that were to maybe highlight what we said before, more on the qualitative side, that really gave this nice interpretative 4-step model. But then they really require these ab initio methods to have a real validation of the model and to make sure that that's really what's happening in the experiments. And so maybe now I would like to discuss. So we also have a poll now. So combining analytical, numerical, ab initio, and experimental method in equal measure, is it really the best route to discovery? So maybe it's also a biased question that after what I just said, but.
Yeah, we could call it again a provocative question. Let's see what the audience will say. In the meantime, we have also some question from Rainer Dörner, which I would like to raise, which is said, is our field really after discoveries? Is not more finding and solving interesting puzzles? Is anyone of the combatants?
Yeah. Yeah, I agree. It is. I mean, it's in one of the later discussion points that I wanted to make, that yeah, we are not looking for new fundamental laws. We have established fundamental laws. We are looking for new solutions to the fundamental equations. So yes, like what happens in new regimes, what happens in new systems, like yeah. So solving interesting puzzles, definitely, I agree.
So I will shortly drop in with the results. So what is the best route? Always combination is supported by 15%, mostly by 41%, and sometimes by 43%, and never by 0%. So you got what you asked for. I have here online like a discussion point from Carla, who said that she thinks it's not a question which method to use. You anyway have to use the computer. The question is just how much time you want to spend in order to trade off between accuracy and predictive power. Maybe we'll come to that anyway in the following up discussion points. And I have one question before we come here, maybe from the question and answer chat from Tom Melzer. The question here is, do you think the range of applicability of a model is not more important than whether it's ab initio, analytical, semi-classical, and so on? Anyone up to that from the combatants?
I think that's definitely true, and we have a discussion point that actually goes over this. So I think maybe we'll revisit this point, or potentially go to the discussion point.
Okay, then hand over.
Do you think we should go to that discussion point, or?
Yeah, why not? Okay.
So essentially, reformulating this question. So we came up with the conclusion that ab initio was quantitative and analytical was qualitative, but we kind of had some ad hoc criteria about what made a method ab initio. So there was some allowed and some disallowed approximations, and this is kind of what I interpreted them as. So there was an allowed approximations were sort of using classical fields, classical potentials, dipole approximation, and ignoring relativistic effects, whereas examples of what I would say were disallowed approximations were kind of effective potentials, single active electrons, and using, say, a DFT empirical exchange function. And I think, in line with what Tom was saying, all of these approximations may be qualitative or quantitative depending on the parameter range. And perhaps we would want a new definition of what we could say is ab initio, that's models with approximations that have well-defined errors for an explicit parameter range, and that neglected physics would be negligible for the parameter range of interest, and other approximations would be well estimated and have a controllable error.
And I think there's a slide for Marie
So yeah,
replying to that.
maybe to complete a bit, I would also argue that there is no real ever ab initio program, that you always need to input some sort of parameter at some point in your code. So be it in DFT method, where you would have to choose the functional, but also basis sets, or in some cases, in many cases, pseudo potentials, but also in wave function methods, I would argue that the choice of the basis set and of the subspace is an arbitrary choice and not a non-important one. But also that the choice to say that single atom or single molecule methods would be ab initio, even though it neglects collective effect like superfluorescence that we've heard of in the nice Nina's talk of 2 days ago, and propagation of light also of like resonant pulse propagation, where the propagation of the light affects the way the next atom sees the interaction between light and atoms, would also be interesting to look at. So it really, I would argue that we will never reach ab initio, so it's really also a good way to define a method.
Can I say something?
Yes.
Okay, so yeah, so that's true. You always need to. I agree with Marie. You always need to introduce some. Make some choice when you start solving a problem. But I think the issue here is how you can control the quality of the result as a function of the choice you make. For example, if you have to input a basis set, well, is there a way to check how you can converge to a stable solution by changing the basis set? And how is this more or less allowed, or like, justified, then do the same for the fundamental interactions? Like, can we do this with the Hamiltonian? Look, I pick a random Hamiltonian and then I change it and then I see how I converge. But what do I learn from the physics? Maybe nothing. Maybe I won't even converge. Maybe I will diverge to a completely different system. So in a way, I think the basis set is like something that it's like, I mean, we can't solve anything exactly. That's our nature. I mean, unless we are hydrogen atom or we have an infinitely big computer that we don't have. So we definitely need to make some approximations or rely on some help. This is, if it is controllable, done in a controllable way, I still think you can very well say that you are doing it in an ab initio way. That's my opinion.
I agree with Marco. So wave function methods work on a finite basis, but it's a basis which can converge to a complete basis. Yes, obviously, if you're not converged, then it's not capturing the full physics. But I don't see how a finite basis that you've checked has converged detracts you from being ab initio.
I don't know if I can answer maybe a bit provocative to that, is when you do try to represent continuum states with, for example, Gaussian wave function, you will probably in some cases never converge. But
absolutely, that's true. So it's our job to look for different bases, like I don't know, grid methods, B-spline basis, like changing the basis in an ab initio method corresponds to searching for new physics. It's like within the method, you use new bases, you want to explore different spaces of in the Hilbert or Fock space as you want, and you look for new solutions. And yes, with Gaussians, you can do great quantum chemistry, but then if you have ionization, then you're well limited. That's definitely the case. Yes.
Should we move on to the first discussion point now? Also, can I briefly, on the point of scientific discovery, I would disagree with what Marco said. I'd say just because something's fundamental, like isn't fundamental, doesn't mean it's not a discovery. Like you're kind of discounting all of other sciences that are based on more fundamental things like physics if you don't call it a scientific discovery unless it's fundamental. So I would disagree with Reinhard Dorner's point and Marco saying it is still a discovery if it's new knowledge that we didn't know before.
Yeah, no. I mean, I think it's a matter of terminology. Maybe Reinhard, and I mean that's how I understood it. We were referring to discovering new laws. You know, like new particles, new laws of nature, new dimensions. You know, something exotic to us. Like we are more like we know the rules of the game, but there are many different way of arranging the pieces of the puzzle that can give infinite number of scenarios, and we know a few of them. Yes, we are discovering the ones that we don't know yet. So in a way, it's always discovery.
Yeah, you can discover new solutions to equations of motion and laws of physics that you already knew.
Definitely, yeah.
I shortly drop in. I get a question from an anonymous visitor, which is also a little bit provocative. The question is whether the single configuration time-dependent Hartree-Fock method can be effectively used to study multi-electron effect in atomic and molecular systems. I mean, it's part of the things you already discussed. I make approximations which are not valid, how to deal with this. Same with the basis set. I mean, something which I can systematically improve.
I think time-dependent Hartree-Fock method, yes, can definitely be used. I mean, it's related to RPA as well, if I'm not mistaken. So, I mean, time-dependent Hartree-Fock is definitely a method that can be used to study multi-electron effect. Yes, I would say so. I don't know about I mean, that one would need to check the level of accuracy, of course, compared to other methods, but.
Question is what you mean with multi-electron effects, what kind of correlation and so on. So.
Yeah, because the time-dependent is the time-dependent part that makes, like you say single configuration, so requiring that each time you describe your wave function as a single configuration, but these orbitals change with time, and therefore at each time it can be expanded on a basis of fixed time configuration. So I mean,
I have some other questions from the chat. One which Bridget Cooper was saying that a Twitter user, Black Physicist, had pointed out that equal measures in the last poll is a bit controversial. And Carla pointing out that if you look at paradigms in our field, they come from analytical model, but need numerical or experimental backing. Maybe some opinion from the discussion, from the combatants here.
I think that, yes, paradigms almost invariably come from analytical models, but it's an interesting question whether we always need to pass through numerics or whether just matching directly from an analytical model to an experimental result is enough to leave everybody satisfied. And I think most people would still want some form of numerical method to numerical validation to be convinced that that's what's happening.
Should we move on to the first discussion point?
So that was a point I wanted to make about the cons that I saw in the question 2 presentation, that approximation was downside of analytical method, and I wanted to argue, maybe also a bit provocatively, that it's, in my opinion, more of a strength, right? Because approximation is really what it builds your interpretation and what builds this qualitative picture that you construct over a physical process. By precisely, if you can remove all that is unnecessary and still get a reasonable agreement with something else, what is this something else, be it numerical or ab initio or experiment, then this is when you really start to construct some physics and some real interpretation. And that's why I want to argue that any method, an analytical method by itself, is not really useful, but it's when you can compare to something else that you're really starting to do real physics, in my opinion.
I would say that this is kind of an idealized view of approximation. It does have a lot of positives to it, but a lot of the time you don't just strip away what you don't want and are left with a simplified picture that kind of models the physics. I think it's very difficult to not lose some of the things that you actually want. And so it's more of a double-edged sword. It, simplifies the picture to understand it, but you're always losing things that you want to describe. And there's often no happy medium where you get this perfect case where it's just purely a strength and we can understand it without losing any information that we actually want.
can I comment on this as well? Just from this point about approximation also goes for numerical methods, I think, as well. It's always good to determine in advance what the sort of critical approximations are that you can afford to make and work within those. And things like SAE, there may be plenty of scenarios where SAE is plenty good, and going beyond it is just overkill, and it's making your life hard from the terms of interpretation, that sort of thing. It may be clouding your interpretation. Things like dipole approximation as well. I mean, I know I'd be a bit stuck if I couldn't rely on a dipole approximation in many cases. So I think it's just establishing critical approximations, and that is what helps you most from an interpretation standpoint, I'd say.
Yeah, I agree with Greg. I also would like to make a comment about what we learn if we had the wave function of the universe. So I wish we had it rather than not, but the problem is that in order to extract all the information that it would allow us to have, it would require probably an infinite time, so we would never benefit from its knowledge. So, it's like too many informations. How much can we handle?
We have it though. We live in it. It's the universe.
One more question from the chat from Jens Biegert. He would say that an experiment is like doing an ab initio simulation in the sense that one can change the boundary conditions, but it doesn't necessarily allow you to disentangle what happens. So here he says analytic, semi-analytic, or hybrid method allow to provide insight. If we do the opposite formulation, if you take ab initio, let's say 2 electron codes, you put everything in, you make kind of a numerical experiment. So what do you learn here?
Yeah, so I think this connects with the second point. Yeah.
In the next slide.
So here I wanted to make a point that that's definitely true, but I mean, I also would argue that ab initio can also help disentangle different effects and be modular. I mean, in a way, when we solve something, ab initio, for example, ab initio can just be analytically or numerically. In most cases, the ab initio Hamiltonian is too difficult to be handled analytically, so we rely on numerical. But we still can input a knowledge of the Hamiltonian terms, and then we can switch them on and off in our computer implementation, and therefore study the effect of different interactions. For example, in the algebraic diagrammatic construction method, which is comes from a Feynman diagram expansion of the polarization propagator, when implemented in a B-spline basis set to study a ionization continuum and implemented on a computer, this offers, for example, the chance of switching on and off dipole matrix element, electron correlation, interchannel couplings, effect of the Coulomb potential, and therefore study which, as a function of, for example, the laser parameters, in which ranges of these parameters, one interaction is most contributing than the other, and what is the interplay between the two. And here I show an example when from one of my calculations. So I calculated the ionic coherence when we strongly ionize CO2 molecule, and to show how the full result it can be decomposed into all sorts of mechanisms: tunnel ionization from different channels, dipole couplings between the different channels, interaction of the ionic system with the photoelectron, different level of treatment of electron correlation, and so on and so forth. We can switch on and off these things in a computer, in a code. The problem is, perhaps we cannot do it as efficiently as if we had the equations written on a piece of paper, because for us, it would require to run the same calculations several different times. And of course, it all comes to how efficiently is the implementation? How does it allow us to use the potential that it is there to use the modularity of an ab initio method?
This is essentially related to the last point of the discussion when you said it's approximation a weak or a strong point. You can do the same here as well, essentially, with what you're saying, Marco.
Yes.
I would partially disagree with that. And it's kind of leading to what made the second battle so embattled, so to speak. In numerical methods, you can often do this, but you can't always. So particularly when it comes to spatial interference patterns or momentum interference patterns, it is extremely rare to have numerical methods that are able to split between the different channels and assign the different channels that are interfering. So sometimes, yes, you can switch things on and off and assign things in a modular way, but ab initio methods are often completely limited in the degree to which they can do this.
Absolutely. I second Emilio's point on this. So, Marco, this is a sort of a perfect example of modularity within an ab initio method. You have 6 switches here on the left-hand plot. You can turn on and off, but you have, in the plot, you have 70 or 80 data points. Is that right?
Yes, that's right. Yes.
So you have, each data point presumably then can be calculated reasonably efficiently. And therefore you have the sort of luxury of modularity enabled because each data point can be done relatively quickly. And as Emilio says, a lot of ab initio methods won't have that type of capability. Each calculation will be so big that modularity can't be afforded.
No, I perfectly agree.
We'll come to the end of the session. I got here the question from the quantum battles, whether it's a time for the final poll. Is there any?
We could go to the final discussion point and or to the discussion point relating to the poll and then launch that poll. So it was this, no, 6, there we go.
Okay, sure. No, this was just an example case that I took from Margarita's paper that she showed in her presentation, where they were comparing the analytical theory 3D TDSE to experiment in HHG of tin plus. And this plot is just an example one I've taken from that paper, where the analytical theory does plenty good. It compares well against the experiment, maybe even better in some cases in this plot, against a numerical TDSE. Now, I work with multi-electron codes. I might be tempted to take a big multi-electron code and apply it to this problem. But should I? It seems like Analytical has a good handle on this, and I'm not sure that numerical simulations of the type that I might do would be required in this case. And after all, analytical theory, it's convenient, it's reproducible, it has a lot of advantages maybe from interpretation point of view. There may be cases, this is just an example, the general point I'm trying to make is that there may be cases where analytical can stand on its own and there's no point in performing detailed numerical simulations. You can apply them elsewhere. And by contrast, there will be problems where you need to really crank the handle of big codes, and analytical will only get you so far. But I think Andy had some more points on this he wanted to make.
Well, just to add to Greg's point, that analytical and ab initio are enabled by 2 different powerful tools. So analytical is more based around mathematical functions. Ab initio is solving fundamental equations with computers, but both are self-standing. You can use both for scientific discovery, and there's no requirement to have both. It's just usually preferable. And of course, probing with these different tools leads to differences in your understanding and interpretations. And I would argue that in different situations, one or the other method may be more useful than the other for pushing forward knowledge. And so at the last part of question 3, we had this kind of symmetric feedback loop. And I would say it's not usually as symmetric as presented. Often one method will dominate, and it may be because it actually works better or because of historical reasons that is the case. Did you want to elaborate a bit, Marco?
Well, I already touched a few points here. I think what I can say is that what I would like to raise is, given that whether we are more experimental or theory driven in our field, and also how and what can we learn from what we already know. And here I have a few examples. For example, what can we learn when we go and explore different systems? For instance, high harmonic generations in liquids or in solids from what we already knew in gas phase. What can we learn when we explore electron dynamics in molecules from what we already know in atoms? Well, in molecules, we also have the nuclei now. And so how do we, in our mind, move from one picture to the other? And what can we learn in terms of spectroscopy technique? For example, when we move from UV or infrared regimes to X-ray, how much do we learn from this? So instead of distinguishing between analytical and ab initio, I would say our discovery is mostly driven by moving from one knowledge to the other. And the knowledge can be both analytical, ab initio, experimental, can be anything.
Maria or Margarita, do you have a kind of answer to these points?
Maybe not to this point specifically, but maybe I would like to finalize something like most of points mentioned above, that maybe when we are studying some process specifically into the depth, we should combine all of the approaches we have in our hands to study it from all of the sides, points, angles, and understand it clearly, which approaches in which regions, regimes work better, which worse, and so on. And then when we apply, come to application of, for example, HEG or ATI, then depending on what exactly we want to get with this knowledge obtained before, we can choose some specific approach. That's it.
Are we ready for the poll?
Yeah, I think so.
So here it comes. Which statement do you agree with more? First one, computing and quantum computing power will advance so much we will not need analytical methods anymore. Second, we do not need such computational power to understand physics, as our understanding is more closely represented by analytical models. So two voting statements.
While people are answering, I didn't want to comment on this when the wording was being proposed, but because I think it's extremely telling. The phrasing in terms of computing power will make analytical theory obsolete, which we may or may not agree with as a community, is not new. It first came up 60 years ago when computers were first being developed in the 60s, and people thought, we have all this computational power, we're going to be able to solve everything. Analytical theory, Bessel functions, throw them away, we'll just be able to solve everything. And the past 60 years have shown that that's not happened. In fact, we place a lot more value on those tools now. So maybe as we are able to solve bigger and bigger Schrödinger equations, as they argued in the battle yesterday, some of those methods will not become necessary and we'll be able to understand well, but it's important to keep an eye out on that context.
So here we have the results from the last poll. So only 11% agree with quantum computing will solve everything. 34% needs everything is analytical, and 55% agree with neither. So this battle is.
Do you know how many people will responded?
I can't see this here. I can't see.
About 43, but I probably added it up wrong.
Okay, thanks. So looks like points are quite clear. How many voters? Yeah, it's 43 it was said. Okay. Thank you very much for this lively discussion. We have seen you convinced both everyone from analytical and the power of numerical things. I have some famous last words before I hand over to the organizers who wanted to make some announcements.
I think I love the last poll because it touched on a cultural war that exists in our field, consciously or unconsciously. Although my opinion would be the last one, that we need both analytic and numerical methods because they complement each other. But this mentality that we go for either one or the other is something you still see a lot. And I think it would help everybody if we can get rid of this front. It doesn't help science. Now, we would like to make an announcement. We're going to take a group picture. So because we cannot do this from our webinar, we have created a meeting with a link that is going to only be shared among registered participants. So the link is on Slack. So now after this session, please go to the general Slack channel and have a look at the link.
The link is also in the chat for this meeting.
Everybody
so you can click
who wants to join, and we're going to have a group picture. And all attendees also have got the link now. It has been shared by Henry. Thank you so much for that. And we're going to have a group picture right now. So thank you all for this amazing session.
Thanks for your discussion and thanks for the combatants.